Hi, my name is Michiel Lambrechts. I'm a PhD student at Lund in Sweden with Anders Johansson as my supervisor. I'll be talking about the formation of the cores of the giant planets, and I will talk also a little bit towards the end about implications on their composition, and that's work I've been doing together with Alessandro Morbidelli in Nice. Okay. So let's start with reviewing core accretion. Essentially, the idea is that you first need to grow a solid, and on that solid core, you can attract a gas envelope. So you start out with some. You start out with something that is like around an embryo that's maybe moon-sized. And at that point, it starts attracting a gaseous envelope. As the core grows, the envelope grows larger and larger. At some point, this thing starts to self-gravitate and essentially collapses, typically around 10 Earth masses or so, and then you set up the conditions for very rapid gas accretion, which then can form your gas giant planets. There are several lines of evidence for this formation mechanism. The first comes simply from our solar system. If you look at the ice giants, their mass is mostly composed of a rocky, icy core. And if you go to the gas giant planets, you find that these planets their atmospheres are very polluted in heavy elements. So heavy elements are the elements with an atomic number above helium. And they likely also have cores, as Roman Revkov also told us. But these days, we can also look at exoplanets to further find evidence for this. The first part simply comes from looking at the transiting planets found by Kepler. So if you plot here on the x-axis the radius of the planet, and you look at the ones with a radius larger than 4, that's the giant planets, and you look and you plot down here on the left axis the metallicity of the host star, that's essentially a proxy of how dust-loaded the protoplanetary disk was. You find that you need disks that were of the sort of same order of metallicity as our own solar system or above to see giant planets. None are found in lower than supersolar metallicities, although this constraint is not so important for smaller planets. So essentially, this is quite curious, right? You form planets that are mostly composed out of gas, but it's very clear that you need solids to form them. All right, and we can even do, I would say, a little bit better. You can look at mass radius models and determine for some of those exoplanets the total mass locked in heavy elements. And what you see is, again, you have to go to supersolar metallicities to find planets, and those all have heavy element masses, about roughly 10 Earth masses. And if you increase the metallicity, those heavy element masses go way, way up, even to the regime of hundreds of Earth masses. Okay, so this gives us confidence that we need to work in the core accretion framework. Now we have to look at what are the essential constraints. There are two major ones. The first one is that we have a lifetime of the disk, which is around, the median age is around 2-3 million years. You can get that, for example, from looking at stars and looking at the SAD that traces the small dust in the disk, and now you compare it to the host star age, and essentially, if you then look, you find something that the disk lifetime is something around 2-3 million years. And even these days, we can do better, right? We can even just image planets around stars of around that age. So as you can see here. So that's one thing. That's the most important one. Then there's another one that Roman is also explaining. We need to be able to form giant planets at wide orbital distances. Maybe the most extreme example is HI8799, where you have planets between 15 to 70 AU. And it's quite remarkable, as already was alluded to previously. HI8799 is a perfectly scaled up version of our own solar system. If you plot the planets one by the stellar flux density they receive, they exactly line up, and you even find an asteroid belt and a Kuiper belt that is essentially exactly the same places. So these are the important constraints. So now we move on to, can we actually form this core that we seem to need to have? Okay. So let me start with explaining this figure here, which will come back a couple of times. So what you see on the x-axis is the mass of the core you want to form, and on the y-axis you see the accretion rate. So if you have the accretion rate, you know which core mass you want to form, you know how long it's going to take, And from that, you can find out whether you can do it within the disk lifetime. So here, this orange region basically marks all accretion rates that are too low to form the core of the giant planet by the time that this dissipates in a couple of million years. And here I plotted the lines marking the planetesimals. So you see, it's a huge failure. Okay? It's very tough to make your core with planetesimals in a standard scenario. The reason for that is that accretion is basically regulated by gravitational focusing. So you have what we call the Hill sphere around the core. That's basically the maximal gravitational reach. Planetesimals enter this region, and most of them are scattered. Only 10 to the minus 4 of them that enter that region actually get accreted. So that is a very low efficiency. Most of the things just scatter past the core. Now, you could potentially increase the accretion rate by grinding down the planetesimals, but this is really a tough game to play. First of all, you need to still form the embryos that start this collisional cascade. That's very tough in the outer disk. And on top of that, you can trap the fragments, you can carve gaps in the planetesimal distribution, and so forth and so forth. It's difficult. The alternative is that you start looking at, instead of planetesimals, the accretion of primordial pebbles, centimeter-sized particles that we already know that live in protoplanetary disks and basically survive all the way till the end. And we know that from observations from, for example, those people here in the bottom. And that is a much faster mechanism. Here we see in red the accretion rates from pebbles, and they fall nicely in this white area here, meaning that we can easily form those cores with this mechanism before this dissipation. Okay, so why is this exactly such an efficient mechanism? I try to illustrate it here with this sort of small cartoon to capture the essence. The point is that when you're a big planetesimal, you don't feel gas drag, you only do gravitational interaction, you essentially just scatter past the core. While if you're a small pebble, you feel gas drag, you dissipate energy while you start crossing the embryo, and that ultimately results in you falling onto the core and accretion to occur. Okay, this was the simple explanation. You can also do this numerically. Here I have in the bottom, you can see what I've done. I've put essentially a box here in a Keplerian disk that turns around, and it basically follows the core, and I track essentially a large population of pebbles around it. And I think I need to press a button here to start moving. Okay, so essentially what you see here is you look down inside the box and you see the surface density of particles. You see some turbulence going on, particles reacting back to the gas on the particles. Here we put the core, and you measure the accretion rate, and you wait till you reach a steady state, and you make the measurement. And you can repeat this exercise for different core masses, and essentially you run the simulation until you lose all your pebbles. So then you get you find out that all pebbles that approach this Hill radius get accreted. The essential idea is that when the embryo is large enough, the crossing time is always your orbital time scale, and your friction time, by looking at pebbles, is also the orbital time scale. Remember, Eugene Chang explained the friction time is essentially the time a small particle needs to react to changes in the gas flow. Essentially also you find if the embryo is again sufficiently large that you excrete all the particle layers, your Hill radius is larger than the particle layer. Okay, so another way to visualize this is in the top here. You start out with an embryo that's sort of like Pluto-sized at 5 AU, and then you see, by extrapolating the accretion rates you measure here, that very rapidly, in 10 to the 4 years, you form a core of 10 Earth masses. And if you start out with smaller things, this is not at all as efficient. You essentially end up in this what we call drift regime, which is not as efficient. So as explained, you need a certain transition mass, some sort of embryo mass to start up this thing. And it's about a factor 10 larger than the sort of average planetesimal you would form by, for example, the streaming stability. All right, so if you want to know more about the accretion of small particles, you can have a look at a poster of Chris Ormel here. And if you wonder more where all those pebbles could come from, it could be a good idea to have a look at Catherine Root's poster. Okay, so now we've covered the first part of, core accretion, now we can have a look at what happens next. We still need to collapse this envelope. So the classical reasoning that goes into there was already developed a long time ago by Mizuno and Stevenson back in the 80s. Essentially, you start out with a core mass, you assume an accretion rate, or better, you take an accretion rate that is self-consistent with the core mass. That gives you a luminosity, then you need an opacity prescription, then you can make an atmosphere model, which I sort of hinted here, temperature profile, density profile. Then you also know what is the mass in the envelope, and you repeat this for larger and larger cores until the point that in practice you find that the envelope mass is comparable to core mass, and your hydrostatic equilibrium breaks down. So then we can make this plot here in the bottom, which you sort of maybe remember from previously, and now I've drawn this gray line here, which essentially means that if you have accretion rates above the gray line, you support an envelope around that type of core, while if you're below it, you don't deposit enough luminosity to have a steep enough pressure profile to support the gravity of the envelope. So what you see here is a classical reasoning. All right, if you're accreting planetesimals and you go past around 10 Earth masses, you don't have enough accretion rate anymore to support the envelope. The gray line is above the black line, and essentially you trigger the collapse of the envelope. All right, so, but now you see that if you go further out in the disk where the accretion rates are low, you actually have very low critical core masses, completely not in agreement with what we find in our own solar system, where we have the ice giants, we have high core masses. But then, if you go look at pebbles, all of a sudden you find you need huge core masses to collapse it. Okay? It doesn't work at all, it seems, but we don't accrete all the time at these high accretion rates. In fact, there is something as a pebble isolation mass. As the core grows bigger and bigger, at some point, you have a back reaction of the core's gravity onto the gas that changes the density profile, essentially makes a pressure bump where you trap all the pebbles, and that abruptly shuts off the accretion, and that allows you then essentially to still collapse your envelope at the right point. So this is what I propose. You grow very fast, then self-consistently you shut off the accretion, and essentially that triggers the collapse of the envelope. So okay, now we have an efficient mechanism ready for the gas giants, but everybody always forgets about the ice giants. Poor ice giants. So here's the other take of it. Okay, so some planets clearly did not reach this pebble isolation mass. If you go to the ice giants, you know, they're around 15 Earth mass, so they didn't reach this 20 Earth mass limit. So what you then can do is that you can pollute the envelope with heavy elements. We are creating here small particles that are likely very icy, and you deposit them one by one in the envelope, changing their mean molecular weight. So that's the alternative. You just pollute the envelope so much, you make it just a heavy envelope, and that lowers the critical core mass. So, all right, so just to give an example, what would this mean for our own solar system? Okay, you have the gas giants here. If you plot them in total, here's the total mass, so then they fall up here. And then here you can plot the heavy element mass of the total mass, so that gives you a handle of the composition. And so there's a huge uncertainty, so that's Saturn, and this is Jupiter here. And essentially they're close to this kind of composition of a pure gas ball, but not quite. And if you would end up here, you would be 100% rocky, icy core. But I show here that the ice giants and Neptunes are sort of in that region, but not quite. They have an Earth mass, or a couple of Earth masses of hydrogen and helium on top of them. Okay, so that's what our solar system looks like, and this is what our model predicts. All right, so you go here, and you look at Saturn and Jupiter. Okay, so you look at the black line, and this is the isolation mass at 5 AU. I perfectly predict the composition of the giant planets based on their total mass. They cross this perfectly. And then if you go look further out in the disk, I took here 30 AU, but you could take something else as well. It's not so sensitive. If you don't reach this isolation mass, which is a little bit higher further out in the disk, you essentially see that you well reproduce the composition of Uranus and Neptune, which is very polluted in heavy elements. So here I think I try to demonstrate that you can naturally explain the dichotomy between ice giants and gas giants from this rapid formation scenario by pebbles. Okay, so here's the summary. I think pebble accretion allows for the rapid formation, of course, of giant planets before this dissipation, even at wide orbital distances. And also is a pathway to naturally explain the difference between gas giants and ice giants. Thank you very much.
Thank you very much. I'm sure some questions for Michel. Yep.
Okay. So your formation times for Jupiter and Saturn like this were pretty short. And you didn't really, I think, say how this would scale to Uranus and Neptune. So if Uranus and Neptune are not reaching this isolation-y mass, how long would we expect them to take to grow to where they are today? And how does that scale with like our expectation of disk lifetime and things like that?
Sure. So the formation scenario that I present here is very fast, and even at 50 AU, we're still looking at only like 10 to the 5 years or so. But of course, we don't know when giant planets start forming in the protoplanetary disk. They might form rather late in the evolution, and so yeah, it's very fast. But
I think Wes had his hand up first. So.
Good stuff. A question for you, though. It looked like the calculations you were doing were for a moderately large oligarch on its own. What happens when you complicate things and put down a possibly realistic disk where there's a lot of oligarchs that have fallen out of whatever other accretion scenario you have that are competing with each other?
That's a very, very good question. I think if you want to do it self-consistently, you have to go look at what is your initial planetesimal distribution, which you're given with. That's completely unknown, so it's rather difficult. But if you start out with any type of planetesimal population, and you then, on top of that one, do this kind of inefficient pebble accretion, you do find that it's actually a population that is mass dominated in the smaller particles, so you have only a couple of ones that run away. So I don't think that will really happen. It's also not so much like in planetesimals where you have to fight all the time for your neighbors. In this kind of scenario, you're dominated by sort of smooth radial drift of particles that's just pretty much unstoppable. The only thing that could happen is sort of filter effect where you say, form one giant planet, then you have another one, the one on the outside accretes everything that comes in. But we find that on average, the accretion efficiency of what you drift by and what you accrete is around 10%. So you can have basically long chains. It's not so bad.
One more question. You can duke it out. Who wants to ask the question? Very close to
Hi, so you explained how to create Uranus and Neptune, but most of the Neptunes we've detected now are very close in, you know, at Mercury's orbits. Can you form them there?
Sure. Everything becomes more easier closer in. I think it is though you can wonder about it a little bit because the isolation mass becomes smaller closer in. But then we have to be a bit honest here also. There might be some migration. It's not always so easy to decide where things form. The only important thing is that you form your giant planet and somehow you don't reach the pebble isolation mass. You start accreting late, or it's a very fast dissipating disk, or any type of other scenario. The important thing is that you here have a dichotomy which really can decide based on the mass whether you become a gas giant and run away or not and you stay small and you become an ice giant.
Okay, thank you very much. Okay.